For most of human history, we have treated time as a universal metronome, a rigid rhythm that ticks forward at the exact same pace everywhere. Albert Einstein challenged this assumption. He argued that the ticking clock we rely on isn't an absolute constant of the universe. Einstein's work revealed that time is actually a flexible physical dimension. Much like a piece of fabric, it can bend, stretch, and slow down depending on how fast you're moving or how much gravity is pulling on you. You don't need to look at distant stars to see this physical warping in action. You can find the evidence by looking at your own body. Our intuition tells us time flows steadily from head to toe, but the physics of our planet suggests a more complex reality. This behavior is governed by general relativity. General relativity is the rule that massive objects warp the fabric of space and time, making time move slower the closer you get to that mass. When you stand on the surface of the Earth, your feet are physically closer to the planet's center of mass than your head is. Because of that small difference in distance, gravity pulls on your feet with slightly more force. This means that at the level of the floor, time moves slightly slower than it does at the level of your eyes. The difference is microscopic, but it is measurable. Over a 79-year lifespan, your head will age approximately 90 billionths of a second faster than your feet. While our biological senses can't feel this shift, it proves that the rate at which we age is tied directly to the gravity of the environment around us. To see this effect on a larger scale, we have to look toward our satellites. In orbit, we reduce the pull of Earth's gravity, but we introduce extreme velocity. GPS satellites orbit 20,000 kilometers above the Earth, traveling at roughly 14,000 kilometers per hour. This environment triggers a conflict between two physical laws. First, we have special relativity. Special relativity is the principle that as an object's speed increases, time slows down for that object relative to a stationary observer. This force tries to slow the satellite's clock. However, because the satellite is so far from Earth's gravity, general relativity simultaneously causes its clock to speed up. In this orbital tug-of-war, the effect of gravity is stronger than the effect of speed. The net result is that the clocks on these satellites tick exactly 38 microseconds faster every day than the clocks we use on the ground. If engineers didn't program the system to compensate for this 38 microsecond difference, GPS navigation would fail within minutes, miscalculating global positions by several kilometers. Our modern world only functions because we have learned to account for the fact that time is physically warping around the planet. If planetary mass can stretch a microsecond, what happens when gravitational force becomes so intense that it's practically infinite? We can only find the answer at the most extreme environment in the cosmos, a black hole. Imagine observing a physical clock as it falls toward the event horizon, the point of no return. As the clock nears the edge, the immense gravity violently stretches the fabric of spacetime. From your perspective, the clock itself begins to distort. You would see the ticking of the clock slow down until it appears to stop entirely. To an outside observer, the clock never actually crosses the horizon. It remains frozen in place as time itself reaches a standstill. This is the final rule of cosmic physics. At the edge of a black hole, the passage of time ceases to exist. These extremes show us that the universal clock is an illusion. We are all traveling through time at our own unique rates, governed entirely by where we are and how fast we are moving through the universe.